Yes, sir. A very good evening to everyone. My name is P. Sivakrishna Reddy, pursuing a master degree at IIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of IIT Hyderabad Student Chapter at Earthquake Engineering Research Center, I want to take this opportunity to welcome our honorable guests, all faculties, industrial people, participants from academia, research fraternity, and all students to join the webinar on advanced topic. Seismic safety of building construction in India under severe earthquake by using passive energy dissipating devices. Today we have the privilege to have with us an expert in field of structural and earthquake engineering who shall be reflecting on theme of this webinar. Now I would like to introduce our keynote speaker for the day, Dr. Pankaj Agarwal, to our esteemed audience. Dr. Pankaj Agarwal is presently working as a professor at Department of Earthquake Engineering, Indian Institute of Technology, Roorkee. His current research interests are earthquake resistant design for masonry and RC structures, post-damage assessment survey of earthquake affected areas, risk assessment, seismic evaluation and retrofitting of structures, cyclic testing of structures, seismic instrumentation in multi-story building, health monitoring and damage detection in buildings. Dr. Pankaj Agarwal has authored one textbook on earthquake-resistant design of structures, published by Prentice Hall of India, New Delhi, 2006. He is continuously engaged in research on structurally sound and seismic efficient construction through guidance and enhancement of test facilities in earthquake engineering. He published a number of research papers in national and international journals, conference, seminars, and symposia. This is a brief introduction of our keynote speaker, Dr. Pankaj Agarwal. Now, before we start the event, a small announcement for all the participants. If you have any doubts, questions, or clarifications, please do type your queries in chat box only. We will have sufficient time for the discussion at the end, where Dr. Praveen Kumar Venkatrao, faculty advisor of student chapter, will be the moderator. Now, without any further ado, we will turn time over to Dr. Pankaj Agarwal. Sir, over to you.
Okay, thank you.
Thank you, Shiva. Yes, sir. You can please share your screen.
First, I will introduce myself. Okay, first I share my screen. This one. Okay, is it visible?
Yes, sir. It is visible and it is also.
My sound is clear?
Yes, sir. Sound is clear.
A very good afternoon as well as evening to all the participants. Myself is Professor Pankaj from Department of Earthquake Engineering, IIT Roorkee. And just my brief introduction is already given by Shiva. Okay. And today I will give the talk on seismic safety of building construction in India under severe earthquake by using passive energy dissipating devices. So basically the keyword of the today lecture is passive energy dissipating devices. It is something new for you, maybe. Okay, how we have to be introduced the passive energy dissipating devices and how to we make our structure earthquake resistant by using this type of the devices. That is the key area or key thought of the my presentation. So first I just introduced, okay, basically the passive energy dissipating devices is based on the damping based. So there are the two type of earthquake resistant type of construction. One is the ductility based and second is the damping based. So there is a slight difference between the concept of these two type of criteria or two type of technique. Basically, in the ductility base, the structure go into the inelastic range and dissipate your energy, basically. And in case of the damping based design structure, the structure is remain inelastic and dissipate your energy. So there is a big difference between the concept of the ductility and damping base. In case of the ductility, your structure go into the inelastic range, okay, large deformation and basically dissipate the energy. In case of the damping base, the structure is remain elastic, less deformation and basically dissipate your energy. So now, whatever the prevailing practice or prevailing code of practice, all are based on the ductility based design. And the new concept basically not new, but maybe the new in India, that is the damping base. So we have to be done the number of experimental study on the damping based techniques just to be introduced in our structures. So that's why we have to be the future construction maybe on the basis of our damping based construction. Okay, either the load bearing type of the structure or RCC type of structure. So with this background, I just give the very fundamental that you already know it. That you already know it in your theory of vibration course in any of the graduate or as well as MTech program. I am not be using much mathematics in the presentation, and very easy concept so that you can be understood very easily what I want to say. Okay, so this is the basically this is our situation, our condition, our structure. If we idealize our structure, any of the structure in a single degree freedom system, that is a very basic concept of a single degree freedom system of mass m, the structure having the mass m, stiffness k and c, and it is subjected to earth to ground motion. This is the condition of our structure, basically resting on the ground, and it is subjected to an earthquake. So your equation of the motion that you already will know it by mx double dot plus kc x dot plus kk. So basically there are the three forces acting on it. One is the inertia force, second is the damping force, and third one is your elastic force. Okay, so and that have to be registered whatever the inertia force in this direction. Okay, once your structure has subjected to the earthquake, the structure start vibrating, and acceleration, velocity, and the displacement will be developed in your structure. Okay, so we have to be control, or we have to be register these vibrations. So basically, the damping-based structure, that is also be called the vibration control. Okay, of our structure. The vibration control means we have to be control the acceleration, velocity, and the displacement. And there are the two ways of doing it. One thing is that we have to be control this type of the vibration, and second thing is that we have to be register this type of the vibration. Okay, so mass into acceleration, that is second law of the Newton, as a force acting on it. And the structure also will go under the displacement. So whatever the permissible limit of your structure, we have to be basically within that. So this vibration we have to be basically either to be registered or either we have to be controlled. Okay. So this structure single degree freedom system can easily be replaced by a inverted type of the pendulum whose mass is m, k, and the damping of our environmental condition. And this is the earthquake motion. And the time period of the structure is 2t by m and by k. Now the question is that first of all you have to be understood basically why we are being so much concerned about the earthquake. Okay, so that is the first reason. So just you have to be just understood what is the level of earthquake forces acting on your structure. So this is just the level of the earthquake under the severe condition. My emphasis is on severe earthquake, basically. So this is the concept, or this is the level of the forces. In case of the severe type of the earthquake, your level of the forces is like that. Red line color, it is visible to you. And under the, basically, in the case of your design type of the forces, we have to be green type. And then for low and moderate type of the earthquake, this is the blue line. And the pre-existing, the code level, this is red line. And your conventional design of structure generally below that line, okay, in this region. So there is a gap, a huge gap between them. If you have to be design the structure by the conventional loading means whatever the dead load, whatever the live load acting on the structure, on that basis you have to be design your structure. So the level of the forces that have to be registered below the dead line. And under the severe force cases, the structure have to be subjected this huge amount of the force. So that's why any design philosophy which is applicable for your conventional design that you have to be stated in your BTech program will not be work in case of the earthquake. Okay, since in case of the conventional, your loading, your level of the forces is much lesser as compared to the severe earthquake. So that's why whatever the design philosophy you have to be adopted in your UG courses will not be applicable to the seismic condition. So that's why we have not be design our structure on the elastic level. In case of the conventional type of the loading, you can be design the structure on the elastic criteria. Elastic criteria means your structure is remain in elastic limit. Okay, whatever the permissible limit is be there, in under that you have to be design your structure. But since the earthquake forces is much higher, So the elastic criteria, neither it will be feasible economically, because since you have to consider these active forces and to design the structure elastically, so your structure become the cost of the structure increase number of times. Second thing is that, okay, since a severe earthquake is a very rare phenomenon, okay, it may be occur during the lifetime of the structure, or it may not be occur during the lifetime of the structure. So just to be design your structure with this severe type of the earthquake motion of large forces, it not be justificable either economically or practically. The second thing is that, again, okay, severe earthquake, if you just see the record of the earthquake motion, so it is hardly 30 seconds to 40 seconds. Okay, so just to be design a structure for 30 to 40, for only that 30 to 40 seconds. Okay, and it is again a very rare phenomenon. So that is not be acceptable for any code philosophy, not only in India, worldwide. So then, what is the solution? Okay, what is the solution is that we have to be basically design the structure for a lower forces. Okay, so that it will become in our permissible limit and basically allow some damage. Okay, allow some damage, and that damage basically yield your structure and allow the deformation of the structure. The large deformation is possible. Okay, large deformation is be there, and but the limit is that the structure should not be collapsed. So that damage basically in engineering terminology we will call plastic hinge. Okay, in simple pendulum you can be understood this phenomena very easily. Okay, since the moment is the maximum at the bottom of that, so the plastic hinges will be formed where the moment is maximum, or the region where susceptible to damage, and the region is where the moment is be maximum. So that region is called technically in earthquake engineering, it is be called plastic hinge. So the plastic hinge basically allow the structure to go in a large deformation. Okay, but large deformation, there is again a definition for the large deformation. The structure should not be collapsed. So that is the limit. So basically, there are the two limits. One is the structure start yielding at the level of dy, that is we call yield displacement, and deform up to the level of du. So du is the maximum. So beyond that, your structure may be collapsed. So there is a limit between the du and dy. And that capability of the structure is called what? It is called basically ductility. Okay, so that is called ductility. So the concept of the ductility basically is the key approach for designing the earthquake resistance of the design. So basically, if we design the structure, we have to be basically determine a lower forces, okay, whatever is be acceptable. So once you have to be design the lower forces, then basically your structure go into the inelastic range, and inelastic range means up to a certain level of ductility. Okay, that ductility is the term, the mu. So delta u upon delta y, we have to be called mu. Okay, so basically the strength and ductility are the two main attributes of designing of your earthquake resistant design of structure. So strength means the lower strength, okay, whatever the actual force acting on it, and second lower forces, whatever the acting on the structure, and second thing is the ductility, whatever is be allowed with you, allow the structure. Okay, so the strength and ductility are the two main attributes that we have to be introduced in our earthquake resistant design of the structure. So this is the door, and that is the, and basically this is the ductility is only be possible when a plastic hinges form. The plastic hinges that you basically allow the structure to go into the inelastic range. Inelastic range means beyond the yield. So that is the characteristic of plastic hinge. So the plastic hinge should be whatever the structure where we allow to develop the plastic hinge at that region where this characteristics to be fulfilled. So it should be yield in flexure, and it has to be the gradual strength by providing the confinement, flexure yielding of the reinforcement, confinement. So they are the main something that we have to increase the capability of your or capacity of your plastic hinge design. So this is the phenomena, okay, just in the single degree freedom system, and just in case of the multi-story building, so that basically concept here to be introduced by the, it is a very known concept that is called strong column weak beam. Okay, since in case of the multi-story building, basically we have to be allow that plastic hinges in the beam rather than the column. Okay, since in case in the formation of the plastic hinge in the beam, it makes the structure more ductile. Okay, since we have to be require the more ductility as compared to the formation of the plastic hinges in the column. So if the plastic hinges form in the column, bottom story of the column, that is we call story mechanism, or it is a kind of a rigid failure, and the value of the theta you see is much lesser than whatever to be the deformation in the story mechanism is much lesser than the beam type of mechanism. Okay, so that's why by making the concept, by introducing the concept of the strong column weak beam, we make our structure ductile. Okay, so that concept basically have to be introduced, the yielding of the beam, and we have to be make the strong column weak beam. And just to be comply this condition, our IS code 1893 and 13920 is be there. And this is the plastic hinge. I again already we show the plastic hinge is nothing. It is the damaged region where the section has yielded. Okay, so it is like that. So we have to be make the capacity of this plastic region so that the deformation is large. So that's why we have to be provide the much confinement at the plastic hinge region. Plastic hinge region is where the possible vulnerable region of your building, okay, where the energy have to be dissipated. So by providing the more confinement, more ductile type of the reinforcement, you can increase the capability of the basically plastic hinge region. The number of factors that is the responsible for increasing the capacity of the plastic hinge region. On that basis, just to be forming the plastic hinge in the beam and column, and by making it more ductile, so then we have to be introduce the detailing of your reinforcement. And this is basically the code IS code 13920. That is the totally basically based on the ductility design. Okay, so whatever the existing earthquake resistant measure provided in the building are based on your ductility concept. Is it clear? Okay, your sound will not become, but
yes, sir. We are getting the questions in the meantime that we will discuss at the end.
Later on, we will take.
Yes, sir. Later on, after completing your presentation, at the end,
This is the first part just to be introduced.
Sure.
The concept of ductility. Now the second approach that basically we are working on it. Okay, so that is the damping based. Okay, how to be made? So there are the two property of the structure. One is the ductility, just to be dissipate. You have already seen it. Your structure has yielded and dissipate your energy. The second thing is that the second property, it is the damping. Your structure is not be go into the inelastic range. Basically, it will remain in elastic condition and dissipate the energy through damping. Okay. So first of all, I just show the few instances where the damping play a very big role. Okay, and you, most of the student, as Praveen told, are the MTech or BTech type of the student. Okay, and they already be know it. Or already be studied your under dam system, critical dam system, over dam system. Okay, in your theory of vibration course or any of the graduate courses of theory based on the vibration. Okay, so just to see how the damping play a role. So that diagram I hope you already studied in your. So this is the first diagram where there is no decay in the amplitude. So that is called undamped structure. Undamped structure means there is no damping present in the system. However, it is practically impossible, but just the undamped system, theoretically, it is possible. We have to just keep the value of the size equal to 0. So that is the undamped system. And second, as we increase the damping, 5%, 10%, 13%, your amplitude goes on reducing. Okay. So 5%, some 10%, 20%, 30%. As the damping level goes on increasing, basically your amplitude of the vibration goes on decreasing. And if the damping reaches up to the critical level, basically, so the vibration is not be possible. Okay. And under the critical case and the over dam system, the vibration is not be possible. So it means if we make our structure like that, the damping reaches to the critical level, so the vibration is not be possible. All the vibration have to be controlled. There is nothing to be do it. Okay, whatever the active condition, whatever the sinusoidal loading, whatever it is, that you have to be apply it, your structure will not be vibrate. And if the damping have to be reaches to up to that level. So this is a very, very critical case. It will not be possible. You have to be increase the damping up to the level of 1, damping ratio up to the level of 1 or more than that. But if the damping level is reaches up to the 1, your vibration is not be possible in your structure. So completely reduce the vibration. And once vibration is not be there, no acceleration, no velocity, no displacement. And your structure is the safe. So this is the one of the very idealized type of the condition is be there. But main thing is that in the present system, some damping is present. That's for example, in case of the reinforced concrete type of the structure, the 5% damping is possible. We will assume the 5% damping ratio. Okay, in case of the steel structure, we will assume the 2% damping ratio. In case of the masonry structure, we will assume the 7%, 7 to 10% of the damping. And in case of the wood type of the structure, is around 12 to 15%. So maximum to maximum, whatever written in the literature is the 20%. But that damping is not be sufficient to control whole the vibration in the system. Okay, so this is the basically we have to be needed it, the supplementary damping. Okay, so this is the first step, the free vibration that I think already all the students have know it. Second phenomena, if the structure is subjective, your single degree freedom system, whatever the previous slide already we show, and subjected to a harmonic type of the motion, so the condition of the resonance may be there. So in the condition of the resonance, your amplitude is be theoretically infinite, but practically the some damping is present, so it has goes on down. So as we increase the damping, basically your amplitude of the vibration from infinite to become the finite level. Okay. So as we go on increase damping 5%, 10%, 20%, your vibration goes down. Okay. Even in the under the condition of resonance. So that is the second instance where the damping has played a very big role to reduce the vibrational or amplitude or vibrational effect. Third extent, during the earthquake, you already know the concept of the response spectra. Response spectra concept, you know the response of a single degree freedom system for a particular type of the damping subjected to a earthquake motion. Okay, so response spectra basically it is the record acceleration versus acceleration velocity or the displacement versus the time period of the structure. Okay, with the different type of damping. So if you have to be plot this response spectra for 0%, 2%, 5%, 10%, 20%. So then you see that your amplitude means either your acceleration, either your velocity displacement goes down as your damping has increases. So basically, damping either in case of the free vibration or in case of your harmonic motion, which is more severe than the earthquake, or in case of the earthquake, the damping play a very, very important role for reducing the vibration or amplitude, basically. So with these three instances, it is clear that the damping is a very enhanced power, or very great power to reduce the vibration. And now we have to be explore how to increase the damping in the system. Okay, since it is the known fact that neither damping can be increased or neither can be decreased. Okay, suppose if your structure has RCC type of structure, So neither you can be increase the damping in the system or neither it is the decrease. Whatever the practically damping available in the system is be there. Okay, so suppose in the case of the RCC type of the building, if we consider it RCC building or masonry building, and suppose the damping is 5%, so the 5% is 5%. Means neither you can be increased the beyond the 5% or neither you can the decrease. Okay, it is not in your hand. Basically, the source of the vibration had to be come from the environment condition, structural joint, and material. There are so many factors which is responsible for providing the damping in the system. And it is a inherent property of the system. Okay, it neither increase, neither decrease. It is not in your hand. If you want to be increased for the damping 5% to 10%, so without any additional feature, you can't be increased, or if you want to be decreased from 5% to 2%, neither increase or decrease. Okay, so whatever the damping present in the system is the percent. But that damping, whatever available, or it also we call the natural damping. Okay, so the natural damping which is present in the system is not be sufficient for control this vibration. Okay, that facts we know that okay, the range of the damping is around 5% to 10% or maximum 20%. So if the damping present in the system is in this range, range has not be control the vibration completely. So that's why we have to be added some of parallel devices in our structural system. And that devices is called passive energy dissipating devices. Okay, that is called passive energy dissipating devices, or it is also called energy dissipating devices in the literature. Okay, and that we have to be provide the supplementing damping, or you also we call added damping. So that is basically these passive energy dissipating devices we have to be installed in our structure. Okay, and parallelly, so that under the earthquake condition, these devices has basically either yield or there are the number of mechanisms be there just to be dissipate the energy and keep our structure remain in elastic condition. So you can be understood this phenomena. It is like a fuse, electrical fuse in your building. So we have to be provide a electrical fuse. If the motion is be, if the current is be much higher, then that fuse has to be basically shut down, and the whole of your electricity line basically remain intact. The similarly, in case of the earthquake, basically these devices either yield, either whatever it is, okay, whatever the damage in these type of devices, and dissipate your whole the energy, and your main structure is basically remain the elastic condition. Okay, so these are passive devices, and these passive devices are based on their different type of dissipation of energy, the mechanism of the dissipation of the energy. The one is the yielding type that have to be done in the metallic type of the temper, and the below figure basically is the devices. Okay, how to we insert these devices. So the energy dissipation devices, the hoop is the flow deformation loop is like the yielding type. This is the material type of the damping. This is the friction type of the damping mechanism to dissipate the energy. That is the viscoelastic type, and that is the viscous type. So these four types of basically the mechanism is generally be available to dissipate the energy. And the devices corresponding to it, from yielding, it is called metallic damper. If the device, if the mechanism is friction, then the device is called friction damper. If it is called viscoelastic type of mechanism, then the viscoelastic damper. And if it's the fluid type of the damper. So these four types of the damper are generally be used to dissipate your whatever the energy. And this dissipate the energy, so we have to be basically make the arrangement to install these devices. So they are the different type of the arrangement may be possible for installing of it. So it is a general arrangement basically given with the seven type of the bracing that is be called or seating belt, or okay, seating arrangement. And we have to just install whatever either the metallic damper or either the viscoelastic damper, either the fluid damper. In case of the fluid damper, we have to use another type of arrangement like in case of the bracing. But in the other type of the failure mechanism, we can be used the inverted V. So the different type of the seating arrangement may be possible. Okay, may be possible. It not be necessary that it has to be provided in this manner. The other possible combination may also be there. But main thing is that the one seating arrangement is required, and second thing is that parallelly we have to be connect this passive energy dissipating devices. So once your structure basically start deforming, so that deformation basically go into your devices, and that devices has start yielded, and once that start yielding, the energy dissipation start. So all of the damage basically concentrated in this passive energy dissipating devices, and your main structure basically become elastic. So these passive energy dissipating devices not only helpful to make your structure active resistant or new construction basically active resistant, but it is very useful in case of the retrofitting of the structure. In case of the retrofitting of the structure means once the structure has the deficient for the earthquake point of view, so you can basically make your structure more efficient by providing the passive energy dissipating devices. So these devices basically we have to be installed in parallel to the main structure, and it had to be deformed or yielded and dissipated energy, or your main structure basically remain under the elastic condition. So it is a very promising approach for protect your structure from earthquake. Is it clear? Okay. So this slide is only just to give the compare of different type of the plastic energy. The basic construction, that is the viscous fluid. Okay, it is the shaft. It is like a shock absorber in your automobile. Okay, the viscous fluid is like a shock absorber. Viscoelastic is again basically they are the type of the damper, and metallic is basically your ADAS type of the damper. ADAS means added damping and added stiffness, just to be increase the stiffness as well as increase the damping in the system. And the friction, you already know it. The friction, the Coulomb friction, generally we have to be use it. That is the mu into n. Mu is the coefficient of friction, and n is the normal force acting on your surface. And with the help of that friction, we have to be dissipate the energy. So that is its hysteresis behavior. Hysteresis behavior is nothing. It is the low deformation behavior. The low deformation behavior of the viscous is basically horizontal electrical type, and this is for viscoelastic. Okay, since it has some stiffness, so it is the elliptical or inclined elliptical type. However, the energy dissipation in the viscous and viscoelastic are more or less the same. And metallic type of the damper, that is the hoop. It may be the different type of the hoop. The behavior may be idealized by the elastoplastic or elastoperfectly plastic or any of the polynomial form. You can be idealize this behavior. And in case of the friction, it is a completely basically rectangular type. And yesterday we have to be tested the friction damper in the lab, and the low deformation diagram is more or less similar to this type of your rectangular block. And this is the model, how to be model our structure. It is by only providing the damper. It is the simple damper, as in case of the natural damping, you have to be just take into account the equivalent damping for the viscous and model as the natural. In case of the stiffness, so we have to be add a stiffening element and damping element. This is the viscoelastic, and metallic. On the basis of that, we have to be model like that. And friction, Coulomb friction model we have. So there are the different advantages and disadvantages. Basically, it depend upon what is your objective of your basically. If you want to be increase the strength and the damping both, so you have to be use the metallic type of the damper. But if you want to be increased only the damping, not the stiffness, then the viscous type of the damper. And if you have to be basically at a very low type of load, some increase the elastic stiffness of your structure as well as the damping, then you have to be use the viscoelastic. And if the friction dampage, because since the load deformation is completely rectangle and the no distribution of the energy and no yielding type of the element is be there, so then you can be use the friction damper. So that the choice of selecting the any of the passive energy dissipating devices depend upon your objective. Okay, so what objective you have? Is suppose if your structure is be deficient under the case of conventional loading and also the earthquake loading, and you want to be increase the stiffness as well as the damping, then the best choice may be the material. But if you have to be the stiffness is be sufficient and you want only be increase the damping, so then the choice may be the viscous. And if the in between, then the viscoelastic. And the friction is again a choice depend. So there is a number of advantages in case of the viscous fluid, activated low displacement, minimal storing force, linear damper. You can read it. Okay, so this is the concept of damping based vibration control mechanism. Is it clear?
Yes, sir.
Okay. So the two concepts, I think it is clear. One is the ductility based and second is damping based. So how to be produce the ductility? The ductility has to be produced in the system through plastic hinges. Okay. In the plastic hinges, you have to be basically make your region more and more stable so that you have to be reform your structure in a ductile manner. So the plastic hinge is the key word for making your structure resistant based on conventional design. And in case of damping based, you have to be used either the passive, any of the passive energy dissipating devices. And it will be basically installed parallel to your structure by some of seating arrangement. So main limitation of the passive energy dissipating devices is that we have to be required the additional space, okay, or you can be say that it has to be entrapped your open space, okay. But architecturally, if you have to be just planning it, then you can be easily be accommodated. But main advantage of your passive energy dissipating devices is number of the time as compared to your ductility based. Okay, ductility based design is not a very reliable type of the solution. Okay, your structure basically intentionally damaged. Okay, one thing. The second thing is that you have to be allow the large deformation. And other secondary effect like your P delta or other type of the arrangement or other effect, side effect, your system may be collapsed during the earthquake. So, so you have to be design the system at a very high risk. Okay. In case of the ductility base. In case of the damping, the number of the advantages. Your structure is remain elastic. It is not be going to the large deformation. Second thing is that your vibration is controlled through the damping. Second main advantage. The third main advantage is that your system has more redundancy as compared to your ductility based design. Okay, your system will become the more redundant, or alternative load path is available in your structure system. If your structure suppose have to be some damage, so it not be collapsed by providing the passive energy dissipating devices. But main limitation by the passive energy dissipating devices is that whatever the open spaces be there, it has to be basically interrupted by the seating array of your passive energy dissipating device. And that basically you have to be taken into account in planning. Okay, so by suitable planning, you can be provide, not be necessary here at each bay you have to be provide these passive energy dissipating devices. So you can basically manage by providing the suitable places. Now we have to be take 3 and 4 basically example. Okay, example means case studies. Case studies means whatever we have developed in our lab facility. So experimental test facility, okay, just to be sure the effect of damping in vibration control. Okay, whatever we have studied it, whatever we have to be talking about all the theoretical concept, okay, unless otherwise something is not be practically tested, it is basically worthwhile. Okay, so the experimental is always be needed for not only for verified your technology or your product. Second thing is that for any of the mathematical modeling or anything, you have to be required the experimental test result. The validation and the calibration basically only be possible through the experimental test. Or unless otherwise you have not been tested any of whatever system, either it is the existing or you have to be new one by the laboratory, it is not be feasible to implement in practical or in not be feasible to implement in field. So the 4 case study I will take. One is the interlink block masonry. So this the first case study is basically to how do we make our structure, basically the load bearing type of the structure earthquake resistant. And the second thing, the second and the third case study basically concentrated on your RC frame type of the structure. And fourth one is how do we make our basically your non-structural element, particularly your infill bar, to basically energy dissipating element. So that's why I have to be consider these 4 cases here. The first is your interlink block masonry. So it is the load bearing. Okay, as you know that my topic of my first this talk basically the earthquake resistant construction in India. So in India, basically there are the 2 type of the structure is there. One is the load bearing type of the structure, and second is the multi-story frame type of the construction. The 90 to 95% type of the constructions are basically your masonry type of the construction, but particularly either the dual part, delay part, or everywhere basically, and around 7 to 10% is only the frame construction. But the situation is be changing it. The frame construction or multi-story building construction is going up, and the load bearing type of structure is going down. But still, the large building stock is be concentrated on the masonry type of the building. Okay, and the few only the 10 to 12% is the RCC type of the structure. So main thing is that how do we make our load bearing structure earthquake resistant by using the damping technique. I will not be discuss it how the conventional masonry building make the earthquake resistant by providing the different type of the band, lintel band, roof band, cable band, your plinth band. So that is the technique which has to be given in your IS code 13935 or 193. There are different codes be given. Here I will not be discussed how to make them earthquake resistant on the basis of the concept of the ductility. But main thing is that here we will discuss how to make the load bearing structure on damping based. So this is the alternative technique to construct the earthquake resistant housing, lower high medium, the concept of the damping. Okay, as I already be explained how it is be different. The conventional earthquake resistant measure based on the ductility, that is the capability to undergo the large deformation without collapsing, while in the present technology the effective use of the damping capability to energy dissipation is explored through friction between the block and yielding of the viscoelastic link. So these are the block we have to be make it in the overlap slotted type of the block, and these are the viscoelastic link element. It is also be here. So these are the viscoelastic link element, and this link element we have to be inserted in the slotted block. A complete video film will be there after the lecture. After this talk, we will show that film. Okay, how do we make our structure? So this is a complete concept of providing. So these are the slotted block. In the slotted block, we have to be inserted the 2 link on the basically on the upper face, 2 link on the bottom face, and one link on the side face. So basically during the earthquake, if you see the movement of the block, so the 2 type of the motion is possible, either the translation or the second is the rotation during the earthquake. Okay, so in case of the translation type of the motion, this the deformation has to be basically passes the the yielding link element, viscoelastic link element, and it start dissipating the energy. And second thing is that if the block have to be tried to be rotated, then the horizontal link will come into the picture and start yielding and dissipate the energy. So basically, the friction is the between the block and the yielding of the link. The two source of mechanism, okay, energy dissipation mechanism we have to be provide or we have to be utilized in this structure. And there is a no mortar we have to be used basically to constructing the whole of the building or whole of the model. Okay. So the friction as well as as well as yielding, the two type of the mechanism, energy dissipating mechanism we have to be use it just to dissipate whatever the incident energy provided by the earthquake. And just in the lab, this model we have to be tested under the shake table condition as well as in the shock table condition. So first I will show the test result on the shake table. So the Department of Engineering has a very good facility, that is the shake table facility, which is the first in India, okay, or even one of the in Asia. Okay, this shake table platform of 3.5 meter by 3.5 meter, and the payload capacity of this shake table is around 20 ton. So up to the 20 ton weight we can be put in the shake table, okay, or you can be say a model up to the 20 ton weight we can be make it and shake it basically on the shake table platform. And these shake table platform basically connected to the servo hydraulic type of the actuator, and that actuator basically apply the earthquake motion. The motion which we have to be recorded in the field, either your Kobe earthquake, Chamoli earthquake, Uttakashi earthquake, any kind of the earthquake we can be basically play in this shake table as in the shake table. So this is the actual photograph basically of the model resting on your shake table. So this is our shake table facility, okay, and we have to be apply that motion. Okay, so this is the base motion, and we have to be recorded at the 2 level, okay, and and under the severe shaking, the motion retain its shape, energy has to be dissipated, no damage. So this is the friction and yielding basically play a big role in the dissipate, and the vibration has basically whatever important in the structure has to be reduced in the energy condition. So this is basically under the shake table. The second we have to be test conducted on this model on the shock table. The shock table type of the motion is again a very severe type of the motion. Basically, the shock table motion is the similar situation as you have to basically heard the name in car manufacturing, automobile manufacturing, that is we call crash test of the vehicle. Okay. So it is the similar to that type of the test. So we have to be apply a very severe shock, okay, to the model, okay, under the impact type of the loading. It is not a earthquake kind of the loading, and we see the result is how the energy has to be dissipated. Okay. So the shock table is a very severe type of shocking. It is like a crash test in the automobile industry. Okay, if the structure passes this type of the test, so you can be safe, it can easily be withstand the earthquake comfortably. So these are the viscoelastic link element of the model, and it is symbolic. Okay, we have to be apply this type of the motion, and if at the roof level it become like that. So you can just see okay, how the motion has reduced. So that is basically the power of your damping mechanism installed in this feature. So that model we have to be tested under the different shock. The first shock is again is severe type of shock, and then the second shock is more severe than the first shock, and third shock is more severe than the second shock. And you can see the result of that. The two force balance accelerator we have to be installed at the ground platform level, at the roof level, and if we apply the motion and we have to record it, this is the imparted motion to the structure, and this is the basically output. So your whole of the energy has dissipated and motion has to be recorded this much. So you can just see it, okay, how the vibration has control or how the whole of the energy has dissipated. And again, we have to be increase the severity. Again, it is reduced. Again, increase the severity. So that is the maximum. That is the shock. And This is the basically result. So this is basically show the effectiveness of your damping mechanism present in the system to reduce. And if you test the conventional type of the model, or I am not be showing the test result of the conventional type of the model, it will amplify the motion. Amplify the motion means if you record the motion at the roof level, it is much higher than whatever the implement in the structure. Implement in the structure. Okay, so instead of amplifying, it has to be considerably or significantly reduce your vibration. So this is the power of your damping. Again, we have to make the two-story type of the model. Okay, in the case of the two-story model, this is the imparting motion. Okay, at the base level, and at the first floor it is reduced, and at the roof level it is again reduced, basically. And how in case of the conventional type, the amplification is there. If the acceleration is suppose 1.5 g, at the roof level it becomes 2.5 or 3. Okay, in case of the earthquake spectral, sorry, in response spectral, the design spectral, you already seen. It has to be amplified, basically. Similarly, in the second shock, okay, the second shock is be there. You have to be apply the shock and reduce at the floor level, and at the roof level again be reduced. So your whole of the motion has to be reduced. Even we have to be put the non-structural type of the element, chair and table here. So even if this type of the shock, there is no movement in the chair. That is to be just we have to be make a circle on it. So it is does not be move any inch. Okay. So the non-structural element. So that the type of the reduction in the vibration. Okay. Similarly, in the third shock, okay, and we have to be applying a very big shock of the acceleration of the 2G. Okay. Okay. However, it is the shock type of the loading, but in case of the actual type of the earthquake, your loading is or your acceleration is around 0.3 or 0.4 type of the 0.4G. And 0.4G. Here we have to apply the 2G acceleration. Okay. And it has to be reduced as a roof level, it is 1.5 around 1, and again it is reduced to 0.5. So this is basically the reduction of your acceleration. And there are number of the advantages of this type of the technology, basically based on it is environmental friendly. So this is you have to be make the block as well as you have to be require the link element. Okay, and it is the low cost. If it is be making the basically it can be make it at anywhere. It is the low cost and with the cost of the brick or something like that, the cost is much lower and easy to be handled. Only you have to be required two things and just you have to be put it, and the 1 day or 2 day you can be make the complete model. Okay, there is nothing is to be required, and it is the clean and green technology, semi prefab or precast type technology, less water consumption. Only your foundation system and the roofing system will remain same, and the other thing you have to be make it very fast and speed the construction at site, high quality, free from the residual and seasonal cracking. Okay, since it is already we are not be putting any type of the mortar, only we have to be put the wrapping, basically just to fill the outer surface, just to outer there. And low maintenance and the so they are the number of the advantages. So this is the first how to be make your structure, load bearing structure, basically make earthquake resistant. The second case study is be based on your metallic damper. Okay, so here we have to be make the ADAS type of the metallic damper, and Naveen has worked. My PhD student Naveen has worked number of time, and other student is also be working on that. The different configuration of the metallic type of the damper, and since the configuration is play a very big role in the dissipation of the energy, the different type of the combination may be possible. Here we are be making the ADAS type of the damper where the two flexor plate and one shear plate. Okay, and this is the basically how to be yield it and create a as the deformation at the deformation in this apply in this metallic damper, it start yielding and dissipating your energy. So first of all, we have to be tested this metallic damper in our lab facility. This is the conventional lab damper. It is the combination of a shear plate and the flexor plate. Then we have to be tested in our test setup, and this is basically the energy dissipation curve of your the load deformation hysteresis curve of the metallic damper. Okay, and this is the curve of your load deformation envelope of it, and this is the energy dissipation by the metallic damper. After that, we have to make a full scale type of the structure. We have the another facility that is we call large scale pseudodynamic test structure type facility, in which we can be tested the full scale 2-story, 3-story, 1-story full model. Okay, these type of the model we have to be tested in the lab. This model is basically building on the hill slope. Okay, and we will test it. But earlier we have to be tested, and this is our testing platform where we have to be put the model and test it under the vertical as well as horizontal actuator. So these actuator is similar to our shake table type test facility, but here we have to be apply the load concentrated places. Okay, and test the model under the lateral load with the help of the two vertical. We have to be apply the whatever the vertical load coming on the structure, and then we gradually increasing the horizontal loading. And the complete load deformation diagram that had to be used for your calibration of your mathematical modeling or another parameter to determine another parameter we have to be doing. So this is the first we have to be tested a simple bare frame under this combination of the three actuator. One is the horizontal actuator, two is the vertical actuator. The role of the vertical actuator is to apply the vertical load. So whatever we have to keep the vertical load constant during the testing, and we have only increased the horizontal load. And this is the complete load deformation diagram. Load deformation diagram, it is the similar to that you tested your material in the lab, concrete or steel. So you have to be obtain the load deformation diagram or stress strain diagram. In the similar fashion, we have to be tested the full scale structure in the lab. And the complete load deformation diagram, we will obtain it. And that load deformation diagram or hysteresis gave the frame. Okay, since it has the elastic part as well as inelastic part, so for your calibration of your mathematical model or calibration of your whatever is the features, it is very, very, very useful. So we have to be calibrate our analytical model. Either we have to be constructed in the OPCs or any other finite element package, or even the conventional type of the package like your SAP and other package. We have to be calibrate of this, and then we apply to multi-story building. Okay, so the calibration and verification is the, as I already been told, is the two key feature for the purpose for testing of this model. And then we have to be basically apply the metallic type damper here, install the metallic damper, and we will obtain the complete basically the hysteresis behavior. So you can see how the hysteresis behavior with the combination of your frame with metallic damper has changes it. And you can see easily basically the difference between the two structure load deformation diagram. Okay, so even your capacity has to be increased the 2 times. Okay, nearly the 2 times of that, as well as the deformation capacity is also be increased, and basically the damping has also been increased. Okay, here we have to be tested the structure forcefully. So that's why we have to be obtain the complete load deformation diagram under the inelastic beam as well. And all the detail is be given in the published paper. The number of the paper we have to be published on that in our ACI journal and other type of the journals. And we can be share the paper if you are interested in the more results in there. Similarly, we have to be make the third type of devices, basically passive energy dissipating devices. I think time is okay. Just cover it.
No, sir, we can continue. We have
okay.
Yeah, yes, please go ahead.
So this is a third case study, the viscoelastic. Viscoelastic is the similar to, we have to be tested in the load bearing structure. Again, this type of the link element, we have to be prepared with the help of this link element, viscoelastic link element. And this link element, we have to be prepared from the radial rubber tire of your radial rubber tire. Okay, the ply part of the radial rubber tire. Okay, okay, this type of the rubber basically is a very, very useful to making this type of the link. Okay, okay, since it has the rubber and the steel wire. So with the help of the radial rubber tire, we have to be make it this. Okay, this type of link element. And radial rubber tire is a copolymer of the butadiene rubber, and it is very good viscoelastic material. So we have to make this the slotted type of basically arrangement here. Just in case of the block, concrete block, we have to make it in the similar fashion. We have to make the slotted arrangement, steel arrangement is there. And in this slotted element, we have to install this or inserted this viscoelastic link element. And the main, basically, the key feature of this viscoelastic damper is that we have to basically make the two steel plates form two steel bearing here. Okay, bearing just to be register your vertical load. Okay, so vertical load is to be transferred easily by this damper, as well as in case of the condition, this link will yield and dissipate the energy. And that damper basically is our patented device. Okay, and we have take the patent of it or under the process. So this is the complete photograph. So this is the sliding type, slide rubber bearing type, just to transfer the vertical load, and for basically dissipation of energy, this link element and combination of it, it is the completely your viscoelastic damper. And this is basically the actual damper which have to be made in lab. And that damper is again tested in the similar to the your metallic type of the damper in our lab facility. Okay, this is a test setup, the same setup which is already be shown it, and its behavior is different than the metallic type of the damper, but it has the number of advantages as compared to the metallic damper. With metallic damper, there is no provision for transfer the vertical load once the element has yielded it. But in case of the viscoelastic element, this damper, we have the two arrangement, one for transfer the vertical load as well as horizontal load. And this is the capability of the energy dissipation link element. As we increase the number of the link element, our capability or our capacity to dissipation energy increases more and more. So it is basically starting from 6 link, 18 link, 36 link, 72 link, or even 180 links. Again, the performance basically of your increase with the load deformation diagram. Okay, and again, its capacity of your structure has to be increased 2 times or 2.5 times than the original structure. So that you have to be basically this result is give the proof to this viscoelastic damper has increased your capacity. Yeah. This is the energy dissipation capacity, okay, of your damper. So you can see at a low drift of 2%, the damper fit model have dissipate much more energy as compared to your conventional type of. And this is the after testing it, or your link has yielded it and dissipate your energy. And after as the output passes it, this link has to be replaced with. Clear?
Yes, sir.
Okay.
Yes, sir.
So this is the number of again advantage. So distinctive load person mechanism, I already we told. It is the two type mechanisms be there to transfer the vertical load as well as horizontal load. And vertical load installation, restoration of a rotated field link element. Here we are using this type of the visco link element, but it is a very versatile type of the damper. You can be used another type of the link element energy. The number of the type of the material available in the market, like your shape memory alloy or other type of the material that are be available. So you can make this link with this type of material and tested it in the lab and showed compare the results with the other type of the material as well. This is the fourth case study. Okay, how to be made. Okay, in the multi-story building, frame, they are the basically the two main elements. So two main structural, one is the structural component and second is the non-structural component. And under the non-structural component, the masonry infill they play a very big role. So how do we make them also be a? So generally, if you just go to the past damage report, so you will find that the root cause of failure of number of the multi-story building is stiffening effect. Just remember the one word or that word. That is the stiffening effect of the infill wall. Okay, the stiffening effect means that during the earthquake, your conventional infill basically apply a concentrated load or a sharp load on your structure. Due to that, your structural element has failed in the shear. So the stiffening effect of the infill is the main or root cause of failure of the multi-story building. Okay. Okay, how and how do we tackle them? This stiffening effect, okay, is the main challenge for structural engineer. And also that the basically infill wall is depending upon what type of the role you want to be take from the infill wall. So sometimes that infill wall is not be taking any vertical and horizontal load, and it will be separated from the main structure system, and it is more prone to the failure. So number of cases the failure of the infill wall is also be make a havoc in during the earthquake. This infill wall has very vulnerable or to in-plane force as well as out-of-plane forces. And just to be take into just to be convert this infill wall to energy dissipating infill wall, we have to be again use the same concept in the load bearing structure in this infill wall. So we have used that slotted block as again the same we have already been discussed in the case first study. Okay, and the same time the link element. So with the help of this slotted block and link element, we have converted our infill wall to energy dissipating infill wall. So these are the slotted block, and this is the infill. This is the viscoelastic link element. As I already been told, we have used the two energy dissipating mechanisms. One is the friction as well as yielding, and with the help of these two mechanisms, we have to be dissipate the energy. So now by converting this infill wall, okay, by energy dissipating, so there are the number of advantages of that. Okay, since this infill wall will not be damaged during the earthquake, it has to be dissipate the energy very well. So it will be basically protect your main structure system, or it will be also be act as a secondary system. Okay, load resisting system for your structural main structural system. Okay, and second thing is that it dissipate the energy. And third main advantage, whatever the failure in the conventional masonry, either it is the in-plane failure or failure is not be possible in case of your energy dissipating. Okay, since the out-of-plane capability of this infill wall has increased number of times as compared to the conventional. Okay, the number of the paper we have to be published in earthquake spectra and engineering structure and other type of the journal. So you can be refer that paper just to see how that infill wall will be beneficial for construction. So again, we have to be tested, number of tested. One of my student Nidhin has done on this work, basically completely full PhD thesis. And shortly it will be available in your platform Sugandha, Superganga. So this is your frame, and we have to be tested. So we just to be install this type of the infill wall. Oh, sorry, Shodhganga. Not good. And we have to be make the some arrangement, okay, like that groove in the shuttering, or okay, so that we have to be make a hook and this groove, and with the help of this groove, we have to be connect this infill wall with main structural system, so that it is be connected throughout your structure system. And that's why its out of plane capacity of this infill wall has to be increased number of the times as compared to your conventional infill wall. In conventional infill wall, we have to be only rely on the friction, okay, connection. But in case of that, we have to be basically inserted the rigid link, and for the help of the rigid link, we have to be connect this energy dissipating infill wall, that is called EDH infill wall, and that have to be. And again, we have to be tested in our lab. The test setup we already will show that. The complete lab setup we have to be make it. And we have to be tested the three different type of the frame. One is the bare frame, then we have to be use the conventional brick infill wall, and then we have to be use the energy dissipating infill wall. So you can be see that in case of the conventional brick infill wall, there is a sharp increase in the force. However, in case of the EDPH, it is the in between. So it reduces the stiffening effect of the infill wall. The second thing is that basically in case of the conventional infill wall, the whole of the wall has to be damaged and dissipate the energy. While in case in the EDH infill wall, the infill wall is remain intact. Only there are some minor disturbances be there and dissipate the energy. So it is the remain intact. So it will also be act as the vertical load resisting system or a parallel system with that. And however, in case of the conventional wall, it is the completely damaged and resistive forces. This is the comparison of that. I will not be going into much detail about that. Okay, since the time is already over. These are the number of the paper and these are the patent award that we have. And the main thing is that whatever the temple we have to be conceptualized here. Okay. However, the idea is being taken from the literature, but main thing is that we have developed our own system and testing and apply in the field basically. And these are the number of publication basically on the viscoelastic, on the passive energy dissipating devices. On that we are working on it, and still number of the PhD student and MTech student are working on that and explore the new type of the damping devices to dissipate the
Earthquake.
Sound is clear?
Natural
Yes, sir. Yes.
that cannot be stopped.
No.
Thousands of people lose their lives during earthquakes due to collapse of man-made constructions. Each earthquake brings many challenges for the researchers. In the developing countries, masonry is one of the most affordable and adaptable building materials. In India itself, which is the second largest developing country, most of the population lives in masonry.
Your audio is muted, sir. Sir, your audio is muted. Can you please unmute that?
Masonry construction.
Yes. Yes, fine.
Worldwide, many researchers churn their minds for improving the performance of masonry structures, especially during earthquakes. The Department of Earthquake Engineering at IIT Roorkee has developed a new, affordable, interlinked block masonry technique in the construction of earthquake-resistant buildings. The technology works on the principle of energy dissipation through damping and is successful in severe seismic zone 5 as per IS 1893 Part 1, 2002. The proposed research rolls over the development of well-designed slotted concrete blocks and viscoelastic energy dissipator links made up of used radial rubber tires, encapsulated between very thin steel plates. These old and used rubber tires are used as viscoelastic material because radial tires are made up of copolymer of styrene butadiene rubber, which is a viscoelastic material. Ply, that is the base part of radial tire, used for making viscoelastic energy dissipator links, has maximum part of steel wires embedded diagonally in the rubber, which enhances stability, strength, and viscoelastic property of the material. It is available at a very cheap cost in the kabadi market, which cannot be recycled easily. Properties such as high strength, high tear resistance, high shear resistance, and high toughness are more effective for the development of viscoelastic energy dissipator links. 3 types of interlinked concrete blocks, that is stretcher block, corner block, and half block, are developed to make possible arrangements of L, T, and cross in the masonry construction. Interlinking of the blocks is done with the help of 2 types of viscoelastic links, one vertical and one horizontal. No cement is used for the interlocking. Rather, the concrete blocks are provided with 4 vertical grooves to restrict translation and 2 horizontal grooves to restrict rotation under severe earthquake loading. The strength of concrete blocks is kept much higher than viscoelastic links for energy dissipation through the yielding of low-strength viscoelastic links and friction between the concrete blocks. The developed technology is tested under severe conditions on shake table and shock table test facility by simulating artificial earthquake excitations. Its seismic performance is analyzed experimentally. A full-scale housing model with maximum load-carrying capacity is made on the shake table and tested under series of simulated earthquake motions as per IS code 1893, part 1, 2002. Peak ground acceleration of 0.18 g and 0.36 g, that is dBE and MCE of zone 5, considering soft soil condition, is applied. Along the height of the model, there is a reduction in maximum roof acceleration as compared to base motion without any damage in the model. The energy imparted is completely dissipated through friction and viscous damping of viscoelastic links. The model retains its original shape and position after the tests. Further, increasing the severity of the test, single-storied and two-storied models are also tested on shock table by giving impact type of loading. 3 consecutive shocks of increasing intensity are applied. In the test results, it is seen that peak acceleration at the roof of model is significantly lower than the base of model without any distress or damage in the model. It underlines the complete energy dissipation through viscoelastic links without damaging the blocks. The elastic plastic behavior of viscoelastic links reveals that the model regains its original position after completely dissipating the energy imparted during the shock test. Besides better earthquake resistance capacity, there are many advantages of interlinked block masonry system over the conventional masonry system. It is more rational and simple. It ensures speedy construction work. It has high energy dissipation capacity, clean construction at the site, and lightweight blocks or blocks with fly ash may also be used in the construction. So, what do we expect from the industry? Industry intervention is required so that well-slotted concrete blocks and viscoelastic links can be readily available in the market, and to spread awareness about the developed technology.
Okay.
Yes, sir. Thank you so much, sir, for the detailed explanation.
My sound is clear.
Yes, sir, your sound is clear.
क्या यहाँ से हाँ हाँ बस आप अपनी क्वेश्चन से
Thank you,
Yes.
sir.
Okay.
Go ahead, Shiva.
Thank you, sir. It was very informative. You have clearly explained the effect and importance of damping for the structures and about different types of passive energy device also, and under which condition they can be used, and also discussed about experimental studies on passive energy devices. Okay, now I request Dr. Praveen to read out the questions to Dr. Pankaj Agarwal.
Sound is
Yes, yes. Sir, thank you so much for the detailed explanations on the different concepts that you have shared with us today related to damping and ductility along with these specific case studies. And we have a number of questions for you. So if you allow me, then I will read out the questions to you, sir.
okay.
The one of the participant is asking that in reality, how to make sure that during the actual earthquake loading, the plastic hinges will form in columns and not in beams?
That concept is the design concept. Basically, we have to be making the strong column, weak beam is the concept. We have to be intentionally make the column much stronger than the beam. Okay, so that the plastic hinges form in the beam. It is the concept you can be understood very easily, just like a chain. Okay, so in the chain you have to be the different type of the links be there, 1, 2, 3, and 4 type. And if we apply a load, so all of the links have to be basically subject to the same force. And suppose we want to be make the chain to be fail at the second link. So if I intentionally make or stronger the other 4 link, more strength or weaker than that second link, so your chain will be fail at the second link. Suppose similarly, if you want to add the middle link or 4th link, so you can be accommodate according to it. So it depends upon the design concept. So on the basis of the design concept, you can be made or you can be ensured that your plastic hinges form in the beam rather than the column by making the strong column weak or vice versa. In case of the beam or in case of the bridges, our philosophy has changed. We have to make the column weaker than the other type of the structure member so that the plastic hinges form in the column. So whole of the concept is basically based on the capacity based principle. So that is the name of the principle that is called capacity based, either design or.
Okay, sir. The next question is, in which case the shear failure is predominant in RC structures? Because somewhere in your slide you have mentioned that we are going for a preferable.
For example, the beam column joint. So beam column joint is subjected to the very high shear force. So whatever the reinforcement detailing you have, basically will not be sufficient to resist that shear. Okay, since the shear is basically dm upon dx. So in the joint design, your dx is very short and change of the moment is much higher. Okay, so the value of the dm is much higher and is subjected to very high shear force. And shear failure is basically a brittle type of the failure. So that's why we have to make the capacity of the shear is much higher in our earthquake design so that it will fail the flexure. And the basic concept of the earthquake resistant design, which mode of the failure you do not like, you just increase its resistance. So all that is basically concept in capacity based design.
Okay, sir. You said that there is a ductile reinforcement which you need to give. What exactly do you mean by ductile reinforcement?
Ductile reinforcement, basically that concept has come from the basically TMT type of the reinforcing bar. Okay. If you have to start idea about the construction, so earlier we have to be used the mild steel. Okay. And second is HYSB reinforcement. That is we call your TOR reinforcement. Third one is called, nowadays it is becoming the TMT reinforcement. So basically the mild steel type of reinforcement, its yield strength is much lower. And just to be accommodate in a limited space is very difficult. So that's why the TOR type of reinforcement has come into the picture. Okay, which has the more yield strength but less ductility. Mild steel has the lower strength but high ductility. Now the third type of the TMT reinforcement, it is the blended with the mild property of the mild and as well as your TOR reinforcement. So outer layer we have to provide the strength and the inner core we have to provide the ductility. So it is called the ductile type of the reinforcement. It has the high strength as well as high ductility. Even if we have to be tested in, the strain is around 25-30 basically. However, in case of the HBIT reinforcement is 5%. So the so much type of the ductile. But main thing is that we will provide the strength at the outer layer and ductility at the inner.
Okay. So the next question is, why the rectangular type of hysteresis loop is formed in case of the friction damper? Is there any specific reason for that?
Specific reason, basically, I think there is a energy has to be dissipated uniformly. That is the mean basically in case of the friction. Okay. So that's why it is a rectangular type. It is just you have to be basically it is a slip between the two surfaces. So it is uniformly acting. So both the surfaces are on the normal forces. So that's why the complete rectangular type of the practically, theoretically, but practically there is a slight variation.
Okay. Variation, right. Sir, is it possible to elevate the damping from a real structure?
It is.
Is it possible to elevate the damping? Because sometimes we refer, yes, increase the damping, because sometimes we consider increase the damping.
So all are the passive energy dissipating devices. That's why we are using it, just to be increase the damping. Okay, since we are increasing energy dissipation, damping is basically comes from the energy dissipation of the system.
Right.
Here we use the parallel energy dissipating devices so that we increase the energy dissipating capacity of your structure, and that we have to be convert into the Xi equivalent, and that Xi equivalent we have to be using your structure analysis.
And usually in most of our analysis, we consider that 5% of damping in, especially in case of the reinforced concrete structure.
Okay.
Why can't we take the other values, maybe 3% or a 6%? Why it is constant always 5%?
Basically, since whatever the damping present in the system, you can't be model it. Okay, you can't determine analytically. Okay, whatever the damping, they are the number of the sources. It is not a one source. It is the environmental source where the structure is standing, your joint, your material, your detailing. They are the number of the factors. So theoretically, to determine if the structure is standing for you, or you want to be determined that how much the damping in the system, you can't be determined theoretically. It only be determined practical. So that's why the free vibration test or any other test for the vibration test, you can be determine the damping of your structure. So there are the different experimental methods are available in the literature, and one of the easiest way is from the free vibration.
From the free vibration
test, you can be obtained. Whatever the graph I have shown in my one of the slides in the evaluation. So that we have to determine, and by the help of the logarithm decrement method, you have to determine the damping ratio. And damping ratio is your whatever the damping present in the system upon the critical damping. And once you have to multiply it, so you can determine the.
But sir, in the reality, all are the cases which are related to the forced vibration, right? Whether the say.
You can be determine any of them.
Okay, but the methodology will remain same.
Basically, whatever the damping is, either you have to be just the free vibration, forced vibration, or any test. So whatever the damping in the system is,
in your presentation,
possible, but it is more or less the same.
In your presentation, you talked about the different type of passive energy dissipating devices like yielding damper, friction damper, viscous and viscoelastic. For dissipating a specific energy, how do we choose a specific type of damping devices? Is there
specific? I already be given a slide where the comparison is be given. It depends upon your objective. Okay. Suppose you want to be increase your system is like it is be deficient in your strength as well. So you have to use ADAS type of the damper.
ADAS type.
The damper is a metallic damper or the viscoelastic type of the damper.
Okay.
The second thing is that in case of the metallic type of the damper, you have to be defined the yield force. Okay, a level of the force to yield it. In case of the viscoelastic type of the damper, the force is much lower. So the ideal device is that which has to be start yielding at a low force or low deformation. Okay. So that your structure is remain elastic and start dissipating the energy. Okay, so that depends upon your object. So every device has own advantage and disadvantage. Suppose a viscous type of the damper. Okay, two type of the damper. So it has no stiffness. It increases no stiffness of your system. It increases of the damping. Okay, so suppose you do not want to be increase the stiffness of the system, only increase the damping. So viscous type of the damper is preferred to us as compared to the other. Similarly, the friction damper. So this is the no yielding something will be there, and the main characteristic of the fracture that whatever the energy that have to be dissipated, it does not depend upon the characteristics of other type of the phenomenon. Basically. So it is we act uniform, and It depends upon your opinion.
And just a follow-up question to the previous one. How do we decide the direction or the location of a damping device that needs to be installed?
Location or where the installation, basically where the deformation is the maximum, related deformation.
Because somewhere you said that it has to be laid parallel to the building direction, right?
Building direction means parallel to the main structure.
Right.
And idealize or structure is a significant freedom system.
Okay. Okay. Okay.
All the vibration, all the deformation we are taking at the one
Going
direction.
in the one direction.
Okay, but main thing is that the relative deformation is be much there. That's why we have to be making the seating arrangement. Otherwise, if you attach the directly the damper with the mass, so it will not work. Unless otherwise the relative deformation is not be there. Similarly, the viscous damper we have to be put in the diagonal way so that the one end is stationary and second is be deformed much higher. So different type of the configuration may be possible, but main thing is that the relative displacement or relative deformation is there. Okay. Otherwise, this type of device will not be used. And once not be used, not be work.
Okay. And having said that, there are so many advantages for the damping of using this passive energy dissipating devices. Still, the use is very limited. So how one needs to improve?
Basically, there are the two reasons. One thing is that the people do not know the damping. Second thing is that our code is ductility based, not coming on the damping based on the passive energy dissipating devices, and more awareness among the people. Okay, and second thing is that the country has no this type of the facility, and theoretically just to develop the any concept is not very true unless otherwise you have, does not show through either experiment or something like that to their effectiveness. So there are the number of basically difficulty of these. And second thing is that these type of the devices basically need the another space, open space. So it hinders your open space as well. And this is another challenge.
So is there any Indian standard code or any other different codes which talks about the dampers? Okay.
But maybe in future it will
And sir, this
what main thing is that the ductility design is not a very reliable type of a solution. Okay, there are a number of assumptions required in it. Okay, second thing is that your structure under the case of a severe earthquake. That's why I am using the word severe earthquake. Low to moderate earthquake, it is fine. Because since in this type of the earthquake, the ductility requirement is much less. But here the ductility requirement is much higher.
Much higher.
Precipitation energy, your structure become unstable, particularly under the P delta effect, and it will be create the secondary effect and maybe the region for the collapse. So under the case of the severe earthquake, and you have to be design the structure based on the ductility, it is a high risk.
Okay.
And whatever the experimental test we have conducted and whatever it is that to be under this application, the failure is basically like sudden failure.
And how economical these damping devices are to be used for RC buildings?
RC building, it is basically, I think it is the cheaper than the ductility based design. In the ductility based design, you have to be provide the more reinforcement or whatever it is in the plastic in region. In the same cost, we can make the energy dissipating devices if you have to be designed or you have to be manufactured in the country. Okay.
Okay.
And
that too in a large scale.
Maybe 1 or 2% cost if we increase structure cost, so it does not matter.
Right.
The advantage is much higher as compared to increase in the cost. But I don't think maybe the cost has increased significantly by providing this type of thing. Main thing is that it must be manufactured in India.
And that too in a very large scale, so that the industry
the cost will come down. And
come down, right. And sir, can this metallic ADAS dampers be used for retrofitting the corroded RC portal frames in marine areas?
We are using, we have to be tested it, we have published the
paper. Okay.
And that these are the frames the retrofitted frame.
Retrofitted frames. Okay. So first, initially they have been damaged, and then after that, these damping devices have been used. Okay. Since you have already shown that the load displacement curves and the hysteretic loads, there is a tremendous amount of the energy dissipation which have been seen there. Right? And sir, how do you optimize? This question is related to the number of elastic links, because you said that as you increase,
all depend upon your design parameter. How much you want to increase it. According to it, you have to select your number of the link element, or you have to design your either metallic damper, friction damper, whatever it is. Okay. So since what yielding force you have to be required. So your structure must be remain in the elastic range. So the design criteria is come out the your main primary structure system. So suppose the primary structure system capacity is 100 kN. Okay, at the failure ultimate. So it is a lower than that. So you have to keep the capacity, it have to be yielded at the much lower forces, so that your structure must not be failed. If you have to increase the capacity, then your structure going in the sticking, and after that your structure start dissipating the.
Okay. So especially in the case study which you have shown, especially in the sliding device, how many these elastic links have been used, sir? Or it is also a variable parameter?
We have to be tested because we have to be making the complete sorted type of the arrangement.
Okay.
And we have tested 6 lane, 18 lane, the multiple of that, up to the 114. And in the last, whatever we have to be retrofit the frame with the 114.
Okay. During the experimental study, have you ever observed any significant damage to your primary structure, especially in the case of a frame installed with the damping devices?
Basically, whatever we have to be tested it, you already be shown in our lab.
Right.
Forcefully to be test the load deformation.
Okay.
Whatever arrangement you have to be there.
Okay.
We are forcefully just to be go into the.
It is going to the ultimate failure.
Ultimate failure. It totally depend upon your actuator. Okay, so we have to give the displacement 10 mm, 20 mm, 30 mm, 40 mm, 50 mm, 60 mm. So the forcefully we will test it. It is not be there, and if the deformation goes on high and high, your structure and everything will be failed. The testing is basically whatever in the real situation, it's not in the testing. In case of the real, your vibration is maybe
that will be on the much lesser side, because as you have already mentioned, in case of the shock table testing, you have tested till 2G, right? But yeah.
Forcefully we are going to be tested, and that.
So in order to evaluate the complete performance of that particular damping devices.
Our purpose is just to make the mathematical of it. So under the non-linear range or other range, how it will be work. And since the damping plays a role up to the elastic range, as the link has yielded or material is yielded, then its role is over, and then structure has to be started on.
Okay. So you mean to say that all these energy dissipating devices which have been developed in the lab, their main function is to take all the load, right, dissipate the energy, and make the primary structure to behave as an elastic one, so that it will be subjected to a lesser amount of the lateral forces due to an earthquake.
Elastically, your system is not be
much ductile. Right. Right.
The dissipation energy will start only through this device. So it is the critical path that we have to make it for dissipation of the energy. Okay. And the design of these passive energy dissipating devices is like that. Okay, whatever the elastic limit of your structure, up to that limit, your passive energy dissipating devices have basically dissipate the complete.
Okay.
And
so that,
your structure and
there is one follow-up question related to this. You already mentioned about the comparison of the bare frame and the frame with the energy dissipating device. Is there any comparison available where your frame is designed with IS 13935:2016 ductile design and one with the damping devices without any?
We have already been designed, we have already been.
Okay.
One of the students is working only on that.
Okay, sir.
We have tested your R is equal to 0, R is equal to 1, or
1, 2,
R
3.
is equal to 5 with metallic
Okay.
damper, and number of
Okay.
and students are working on it. Basically.
Okay.
Technically based as well as your damping.
Okay, sir. So the next question is there any standing loading pattern for the friction damper? Because the FEMA 461 shows the increment amplitude. So
you can follow any of the different code. They have to make their own code.
right.
Basically, main thing is that after all, as my experience with that, it does not matter much.
Okay.
You follow the 461 or whatever it is, you can make your science series according to it. So there is nothing basically science behind it. The main thing is the code deformation of your device.
Okay.
It will be what?
So the last question of the day is, does stiffness of the structure decreases significantly with the use of this linked elements in the infill wall?
In the link element stiffness of
the last specific case which you have showed, where the interblock elements have been used with the linked elements. So because of that, the stiffness
stiffness basically during the earthquake. During the earthquake, if you have to just study the damage report, past damage report, your conventional infill work as a diagonal strut.
Right.
That have to be convert the frame into like a truss, and stiffness has increased number of times. Okay, so once the stiffness has increased, the forces are affected according to it, and your member has to be fail in shear, basically. So that is the root cause of failure of number of the multi-story building. The second thing is that the infill wall, if you have to just compare the stiffness of a bare frame of around 4 meter by 5 meter height, and if you have to insert a 4.5 inch thick conventional infill wall, however, it depends upon the material property of infill wall as well as your frame structure. It is increased around 65 times. So that type of the stiffness has to be increased. And that has to be completely altered. The force distribution. For example, in case of a 5 frame will be there, and we have to be designed equally for that. Okay, and the force is F by 5, F by 5, F by 5, F by 5 will be there. And we have to be inserted the infill wall. So the force distribution in that frame is completely changed. Both the frame will take the whole of the load, and the remaining frame do not take any type of the load. So the distribution of the forces has to be changed completely. That will not be done in case of the energy dissipating infill. So the energy dissipating infill wall does not increase any significant. However, slightly it will be increase the stiffness, but not significantly increase the stiffness of the frame. So the load distribution pattern will not be changed during the. And all the irregularities, you have to be study the IS code 1893. And there the number of the irregularities will be given. Your strength irregularity, stiffness irregularity, soft story. All are only due to the presence of the infill. So these type of the irregularities are eliminated if you use the energy distribution instead of convention.
Sir, is there any specific change that can we expect from the new version of IS 1893 with respect to energy dissipating devices?
Energy dissipating, that I want to say, it depends upon the.
Okay, sir. Okay. Okay, sir. Thank you so much for clarifying all the queries and the doubts which have been raised by all the participants. And I'm really thankful to you for sparing your precious time and accepting our invitation, sir. Now I over to Shiva.
Okay,
Thank you, sir.
Thank you.
Thank you, sir. I also want to thank all the participants for making this event a grand success. And I hope all your queries have been clarified. Now I'd like to call upon Ms. Minarvi to address the vote of thanks. Thank you.
So, good afternoon, everyone. Good afternoon, everyone. My name is Minarvi Anupam, and I am pursuing MTech in Computer Aided Structural Engineering at IIT Hyderabad. It's my privilege to propose the vote of thanks on behalf of IS Structi IIT Hyderabad student chapter for this occasion. First and foremost, I would like to thank our guest speaker, Dr. Pankaj Agarwal, for sparing his time to grace today's webinar. Sir, I thank you for sharing your valuable knowledge on the topic seismic safety of building construction in India under severe earthquake by using energy dissipating devices, which is of great interest to all structural engineering community. Sir, the insight we received today about the building construction, that is the response of structure during an earthquake, how the dynamic response of a structure is idealized to an equivalent single degree of freedom system of mass stiffness and damping, level of forces under severe earthquake conditions, the elastic response in structure, the characteristics of plastic hinges, and we saw the classification of failure mechanism in a frame structure. Further, you discussed about the various energy dissipating devices, their hysteresis behavior, and how these devices improve overall damping and stiffness of structure. And further, we saw various case studies. So thank you, sir, for sharing your knowledge on various topics. Now, I would like to express our heartfelt gratitude to our mentor, Dr. Praveen, for his valuable guidance and timely suggestions. My sincere thanks to Mr. Srikant, our IT team, Ms. Babita, and Ms. Grace, our design team, for providing all the logistic support, help, and assistance. I would like to thank our program coordinator, Dr. Sunita Palisari, for her continuous encouragement. I also thank all those who have directly or indirectly helped us to make this event successful. My special thanks to all the participants for their enormous cooperation. Last but not the least, I also want to acknowledge the effort, support, and cooperation of my entire team in making this webinar successful. Finally, I want to end this program by extending my sincere gratitude to all of you for being with us. It was indeed a great pleasure. So, this concludes our webinar. We appreciate your participation and hope you learned something from this webinar. Thank you, sir.